Greetings, campers. So we are back, and so we are approaching hopefully somewhere towards the end of our first week here online, and I hope it's going well at this point. I'm actually recording this video on Monday, so this may be a little bit premature to work out some of the bugs. So some things will get worked out as we go along. But I know there's a few of you that have really been working hard to kind of get ahead of things. So maybe I'll put these videos up a little earlier than some of you need them. But I'll try to keep them brief, keep like a bunch of announcements, like housekeeping, like I do pretty much at the beginning of every lecture to keep things normal. Also, I tried doing something with having the PowerPoint slide over here and then doing notes here. I think that's going to be a little bit too busy looking. I can still try to do that. So we're going to try something else where you essentially copy down definitions from the slides, read the book ahead of time, and then I just supplement it with notes and working out math problems. So you can tell me if that works out. Okay, so housekeeping. So we're approaching the middle of the week of our first week online here and transitioning to have a good ending for this first week, so really stick with me here. So at this point, you probably signed and uploaded your honor code by now. Hopefully you've done that. And uploaded problem set number 4, the last problem set from kinetics. A lot of you did that really early on. And then I haven't done this yet, but I'm going to ask that you then submit a kinetics quest, so like the Friday quiz. Let's just stick to that so we can try that out by midnight. I think I'm going to do that by midnight on Wednesday. So those are the 3 things that we should have taken care of, except for the kinetics one, by Wednesday. So by Wednesday, we'll have a nice clean break and we can continue on. Okay. What I have here is looks like a long bullet list, but it's not that much. And this is on D2L, both on the content tab on the side of D2L to end week 1. And I've also made a checklist out of these, so you can check boxes as you go along, since some of you said you like that. So the big thing this week is to take exam 2. Now, hopefully this will stick to the same schedule here, and if it doesn't work, we can work around this. So I'm going to give you till noon on Saturday to submit exam 2. Now, what does that mean? That means if you have a printer, you can print the exam and write your work there and then scan it and upload it. If you don't have a printer, you can simply download the exam, record your answers on separate paper, and then upload it. And this is going to be a little awkward to do an exam, but I'll ask that you on the exam you put the time window where you took it, and we'll try to keep it to about a 2-hour time window. I know it's an honor code thing, work on it on your own, don't divide the labor up and combine answers, anything like that, or talk with a study group online. That's part of the honor code, so I'm not going to go through all that. So that's the big thing, that's the big chunk, that's exam 2. And you already have a checklist for that. There is nothing on chemical equilibrium on exam 2. It is only solutions, colligative properties, and kinetics. Those 3 things, you have the checklist already. Okay, the rest of this then transitions into the next topic, which is equilibrium. So a few things, just some simple stuff. Download chapter 13 slides and chapter 13 homework. Those are already on D2L on weeks 9 and 10. I didn't upload those or anything. Just go to the weeks 9 and 10 like we would have had if this pandemic didn't happen and download those documents. Fine. The first slide, the first slide from those electronic PowerPoint slides are the same as they always are. It's a bunch of definitions. They're important definitions, but copy those down. Go take a look at the book, because the book is probably going to do a lot of what I'm about to do on the board. So what's on the board might just be supplementary, which is great. So take a look at sections 13.1 and 13.3. And when I put read in quotes, that means read it, but then do the problems where you know the answers, and then the check your learning problems where you can do the problem and click on the link or click on the window and it shows you the answer. Those are really good to do. Watch this video. And then equilibrium problem set number 1. So here's the equilibrium problem set. It's chopped up into 3 chunks. The first chunk won't take us very long. Problem set, I mean. Problem sets 2 and 3 will take some time because they're more complicated math problems and we'll need to spend more time on those. And I may end up changing this so that we can not only do this for the rest of the semester. I don't think that'll happen. Okay, I'm gonna have that by midnight on Sunday. Again, all of that is on D2L. All of that is on the checklist, but if you want to write that down on your own, that is fine. Okay, so I'm probably off camera right now. So let me supplement some of these notes from chapter 13. So if you haven't done all this stuff, stop the video, do all this stuff. Make sure that you copy down the definitions. I don't think my notes are going to make as much sense unless you do that. So get to these 2 bullet points before you continue on. If you have to stop the video and take some time to do that, go ahead. So stop. Oh wait, okay, I'm not going to do that. And let's go ahead and get started. And just so that you know what I'm doing here, I've kind of got my computer on over here, so I kind of know what the slide is like that you're looking at, which you can also do. If you prefer just to look at the slide and look at my notes, kind of copy them back and forth, that's fine too. If you want to do that coordination on your own. Again, I don't think it's going to work out great here. I'm going to check to make sure the camera's recording properly before we get going here. Okay. So I think this will work. All right, so we are in chemical equilibrium. It's Roman numeral 5, and I'm just going to give you a few examples here. And I'm probably going to go pretty fast here because all I'm doing is reinforcing some basic definitions. All right, so we can get rid of all this now. So an equilibrium, it's dynamic and it's reversible. So I'm going to show you some examples of that. So it's dynamic and reversible. That's one of the characteristic features of a chemical equilibrium. So the first example of an equilibrium that I have for you is something pretty simple. It's a saturated solution. And what that means is a solution where you can't dissolve any more solid in it. It has the maximum amount possible. So I'm going to use some things we've done before. So glucose is a simple monosaccharide, a simple sugar. So when you put that into water, it's a solid, and then in this direction, that is not dissociation, but dissolution. It's dissolving in water, and that turns into C6H12O6AQ for aqueous. Okay, that's fine. If it's a saturated solution, and it will also have an equilibrium going in this direction. So you'll actually have some sucrose going from the aqueous state back to the solid state. It's actually kind of interesting to see that, like little solid crystals falling out of the solution. And that's called precipitation. So it's dissolution, dissolving in water this direction, precipitation, crashing out or forming a solid going in that direction. Okay, that's an example there. Glucose, another one, oh, and this, by the way, is a covalent compound, so we don't break up the carbons, hydrogens, and oxygens into ions or anything like that. It still stays together. An example that we know all too well, and that's sodium chloride. That does break up into ions, but it's the same idea. So going this direction, you get sodium +1 plus Cl minus. And in this direction, that is dissociation. And in this direction, it's still precipitation. By the way, PPT is a perfectly reasonable abbreviation for precipitation. So in this case, if it's ionic, it breaks up into its component ions in the dissociation direction or dissolution, and then they recombine to form a solid in the precipitation direction. But the point here is, this is an equilibrium. It goes this direction and this direction, the forward direction and the reverse direction simultaneously. It's not one then the other. It is a dynamic, reversible process. So saturated solutions, those are the first examples of an equilibrium that I'm giving you. The second example that I'm giving you is a liquid/vapor equilibrium. And we've talked about this one before, something like ethanol or methanol. We've dealt with these in labs. They go from a liquid to a gas very easily. Those are called volatile organic compounds, VOCs. So, okay. So there's liquid ethanol. We've used that chemical formula before. So in this direction, when it goes to a gas, we call that vaporization or evaporation. Okay, that's a phase change. It's a change of state. But going in this direction, well, you already know what that's called. When it goes from a gas to a liquid. That's condensation. Again, so the point here is it's an equilibrium, and you have an equilibrium between the vapor and the liquid, and it's constantly going back and forth. Okay, I'm just going to check the camera to make sure this looks okay. Good, good, okay, that's looking okay. And I can probably take up more of the board and be a little bit more efficient with this. So give me a second, I'm going to erase this. If you want to check out the book, do something like that. I think I can take up a little bit more space and leave a little bit more information here. Okay. So, connecting equilibrium to what we've done with rates. So, equilibrium and rates of reaction. The whole point of kinetics was how fast does a reaction occur? Okay, well, let's use the example here that we did before of hydrogen peroxide decomposition. And oh boy, did we talk a lot about hydrogen peroxide in the last chapter. Three-step mechanism, elementary steps, catalysis. We talked about all that stuff here. So, hydrogen peroxide decomposes into water and oxygen gas, the bubbles on the inside of a bottle of hydrogen peroxide, if you've ever paid attention to that. And if it's an equilibrium, it goes in this direction as well. So this would be technically a decomposition going in that direction. And what would it be called going in this direction when two molecules come together to make a bigger one? What's that called? Well, that's called, technically, a synthesis. So it's decomposition in that direction and synthesis. This is called the forward reaction. This is called the reverse reaction. RXN being an abbreviation for reaction. So this is generic. So the reaction going in this direction is called the forward direction, forward reaction, and then the reverse direction. That applies to any chemical reaction, not just hydrogen peroxide decomposition. And then for an equilibrium to occur, well, it's the rate of the forward reaction equals the rate of the reverse reaction. They're equal. That's what an equilibrium means. The rate this direction is equal to the rate this direction. And we all, you might remember this, that we can also substitute in something we learned from the last chapter. Now, I'm not going to dwell on this too much. We call these differential rate laws. So if we wanted to talk about the differential rate law for the decomposition of peroxide, remember we put the rate constant in front, and the F's there just for forward, times the concentration of peroxide raised to some power, called the order of reaction. Now we did a lot with this one. We figured out what the order was. I think it was first order. We figured out the units on KF, so I'm not going through all that, I'm just reusing this in symbols. But we can also write the rate law going for the reverse reaction, where it would be the concentration of water raised to some power, called the order of reaction with respect to water, times the oxygen concentration raised to its order as well. And that would be the K for the reverse reaction. So it's the differential rate law going this direction equals the differential rate law going in this direction. That's not a hugely important point, but it's something I may end up using a little bit later. Okay. Another thing in the notes on that first slide, I don't know exactly where I am on that slide, but that's okay, is that at equilibrium, when it's reached, the concentrations of every chemical, reactants, products, remains constant. That they don't change, that the water is turning into peroxide, peroxide is turning into water, but the concentration of the water stays the same. The concentration of the oxygen stays the same. The concentration of peroxide stays the same. They're constantly cycling back and forth, but they're stable concentrations. That's something that's very important to know. So where did I want to put that? I'll put that over here. So that's another characteristic of an equilibrium, is that everything, the concentration stays the same. The thing I want to point out right away is that doesn't mean the concentrations are equal. A misconception about equilibrium is that equilibrium means this, and this always have the same concentration. That is not true. Equilibrium means that this, and this have a constant concentration. But we're going to work that out later. Okay, so an example that I wanted to do here was pretty straightforward. We've done this one lots of times this entire year. Is so I think I'm going to slow down a little bit. This first video is going to end up being really, really long because it's all definitions. So I'm going to slow down a little bit. We've seen this equation before. Hydrogen reacting with nitrogen to produce ammonia, it would be synthesis in this direction, decomposition in this direction, and just applying what we just learned, the rate of synthesis would be equal to the rate of decomposition at equilibrium. And you might recall that we represented this with a graph, where we put concentrations on the y-axis and time on the x-axis. This is how I introduced kinetics, and ammonia would go up and eventually level off. Nitrogen, now let's see, I'm going to try to do this to scale. Nitrogen is lost at half the rate ammonia is produced. That's a kinetics concept. So let's see, I'll just start that here and that here. So you have nitrogen, and then hydrogen is lost at 3 times the rate that nitrogen is lost, so it's going to be really steep. I'm not too worried about that at this point. We've covered that already. The point is this. When all these are stable, that's equilibrium. When those concentrations no longer change, and they're constant, but they're not the same. That's very important. They're not the same. So this is called the kinetic region, if you will. This is called the equilibrium region. Yeah, I'm going to put up another example here. Wow, this first set's going to get really, really long. So take a break, stop the video if you want to. I'm going to leave that example here for constant concentration and do another one over here to set up some math we're going to do later. what's coming here is a preview of coming attractions. Whew, we can't forget anything in chemistry. A weak acid, okay? Well, weak means it only partially breaks apart, like a weak electrolyte. A weak acid only partially dissociates. And if something's an acid, that means it gives us an H+, which is called a proton or a hydronium ion, in solution. So weak means only partial dissociation. Acid means it gives H+. And the classic example is acetic acid. And we've talked about this one before. All right, and let's, there's different symbols for this. That's one way of drawing acetic acid. Another way you'll see in some books. Oh, by the way, this is a weak monoprotic acid. So it gives off only one hydrogen, H+, every time it dissociates. And it's, well, which one is it? Well, in this formula, it's that one. In this formula, it's that one. We draw it so it's specifically showing the hydrogen that's dissociated. An abbreviation that's often used, and if you're in the lab, this is an abbreviation you'll see in the case studies that I did, is something like this. So these are three ways of representing acetic acid. It's a weak monoprotic acid. And how would we write the equilibrium? I'm going to use this symbol. So it's okay. Well, so this is how we would represent the equilibrium. Okay, so C2H3O2 is acetate, which has a negative charge. It's a weak acid, so it gives up H+, that's what makes it an acid, and it's weak because it only partially dissociates. If I did this for HCl, hydrochloric acid, it would just be one arrow, because that's a strong acid. There is no equilibrium, it just goes this direction. So weak acids, by definition, are in equilibrium. Okay. Why am I doing this? I want to show you some math here. I think this may take a little bit too long, but assume a 1.0 molar molarity solution. Okay, I'm going to set this up for you. We're going to do a lot of these. These are called ice tables. Initial concentration, change in concentration to reach an equilibrium. Where do the concentrations start? How do they change to reach equilibrium? And what are they at equilibrium? An ice table. So I'm just showing you one example here. So in this case, you pick up a bottle in the lab and it says 1.0 M with this formula. What does that mean? Well, that means that we assume, oh, by the way, these are all polarities. So the initial concentration of this molecule in its associated form, it has not dissociated yet, is 1.00 moles per liter. And we're using our imagination here. This is a fictitious initial state. We can't hold this and freeze this in time. We're assuming that the concentration of these two ions to start off with are 0. That this is not broken up at all. Okay. Well, some of this has to break up. How much? I don't know. When we don't know in science, we call that a variable. So let's assign it a variable, x. Well, this is going to go down by some amount because some of this is going to break apart. So this is going to be minus x. If you notice, every time one of these breaks up, you get one of these and one of those. Now, these are both the same. It's not like this molecule is half or anything like that. Every time some of this breaks up, you get the same amount of H plus hydronium and acetate ion. Okay, so whatever this goes down by, this has to go up by the same, just for this example. So then at equilibrium, well, it's the initial minus the change. It's the initial, well, 0, plus the change, just x. 0 plus x is x. 0 plus x is x. So where we're headed is solving for x. We're not really ready for that yet. And then you may just want to take a break with these videos. This one's really long. Okay, so if this is a weak acid, it's really, really small because the X isn't going to change very much. Most of it is going to stay like this because it's weak, it doesn't dissociate very much. So just keep that kind of in mind. This is the kind of problem we're going to do in the next video. Okay. And let's see where we are. I think, actually, what I'm going to do is to maybe break these videos up a little bit, but I'm going to keep going with this one. So if you want to take a break, and that's enough for now, that's fine. Mark your time and come back. But I think I am going to keep going. I know I keep changing my mind here. All right, the next topic is thing that you see in your notes, is that an equilibrium will try to maintain itself. What does that mean? That means if you disturb the equilibrium, it will try to return to its original state. Those of you that have had a lot of biology, you know that your body has this concept called homeostasis, where it tries to maintain what it has. And a lot of energy goes into maintaining homeostasis. This is kind of the chemical version of that, is that if you stress, if you change, if you influence the equilibrium, it will do something to react to try to go back to where it was originally. Okay? And that whole idea of an equilibrium reacting is called Le Chatelier's principle, or what is that I'm calling it? Le Chatelier's principle. An equilibrium responds to an external change. Most books call it a stress. I don't really like that word stress, but it makes the point. I'm just going to show you some examples here. There's a lot more in your book. I think your book will be better at this than I will. And let's stick with examples we already know. Fun. This is an equilibrium, and let's consider some stresses. One thing you are going to do, I think, in one of the case studies for equilibrium, if you're in the 126 lab, is you're going to look at this one a little bit. So you'll see this one in lab a little later. I wrote this on purpose. Let's consider some things. Your book has a great description of this. This is called the Haber-Bosch process for making ammonia. We've talked about this a ton. So what happens with this reaction is hydrogen and nitrogen combine to make ammonia. And this is what you want. This is what we want. This is what we want. This is the product. So you want to remove this as it's being made. And one way to do that is to have some kind of a cooling mechanism. And you'll see this in the book later. So it'll cool this down and condense the ammonia into a liquid. So you're constantly removing the ammonia from the equilibrium. Well, what happens there? If you remove the ammonia, the equilibrium wants to replace it. How does it replace it? By reacting more of these two. By reacting more hydrogen and nitrogen to replace the ammonia that's lost. So more H2 and N2 react to replace the ammonia that is lost. Well, that kind of makes sense. You constantly want to make more of that, so remove it, produce it, and until you run out of these things, until you've destroyed the equilibrium, which is what will happen. But at equilibrium, that's eventually what will happen. Oh, by the way, that's called a, oh, excuse me. That's called a shift to the right, because the reactants are turning into products and shifting to the right side of the equilibrium to replace the ammonia in this case. That's a shift right. The opposite would be a shift left, and I guess a shift left could occur. What if I added a bunch of ammonia? Okay, I don't know why I would do that, but say something happened and a bunch of ammonia came in from another source and increased this. Well, you want to decrease that, so you shift it this direction. In fact, you know what? I'm just going to use that example. So what if you have this? This would be a dumb idea. This is a dumb example, because why would you do this? Okay, well, let's say there's some mistake in the industrial process and some ammonia comes in from another source. Well, if that's the case, more of the ammonia that is going to decompose. Okay, therefore, more H2 and N2 will form. That's the only thing that can happen. Equilibria can only go this direction or this direction. They can't do anything else. That's it. And this is called a shift left. Okay, so basically Le Chatelier's principle says if you stress a system, it'll either shift to the right or shift to the left. And there's different kinds of stresses. I only showed you two examples here. Either removing a chemical or adding a chemical. Other things we can do, change the pressure, change the temperature, and that's about it. I'm not going to go through all that right now. This is introductory, and it's, as I've said many times, it's getting a little long. So that's called Le Chatelier's principle. Look at your book for some examples there. And I think I'm going to not put more examples right now like I would in lecture. Okay. We are getting to the point where I think that's going to be enough for this video, possibly. Enough to kind of get you started. A couple last things. And this is turning into like a whole Monday or Wednesday lecture. All right, I think the last couple things can be pretty straightforward here. And then I'll probably end up coming back to this with some homework problems and homework help a little bit later. I think that's probably what we'll end up doing, is a homework help video as well. Okay, a couple things. Not everything's in equilibrium. So that's a fact. Okay. Things that have the label strong, strong acids, strong electrolytes, that aren't saturated. That's kind of one thing I have to be. Those are not necessarily equilibrium conditions. So some examples: hydrochloric acid is 100%. Those are aqueous. I'm not going to write those. Strong acids, completely dissociated. Monoprotic, 1H plus, diprotic, 2H pluses. Monoprotic, diprotic, good words. NaCl, assuming it's not saturated. Oops, that's not right. Breaks up the powder. One of your homework problems asks you to look at things that don't dissociate completely, and I'll leave that for the homework. Yeah, I think we'll just kind of leave it like that one. So strong acids, well, I'll put this one up here. I made a small oversight previously when I showed you the ethanol vaporizing being in equilibrium with the liquid, so a liquid-vapor equilibrium. That would only work if I had a top on a jar of ethanol. That would be a closed system, okay? Because if I have a jar of ethanol just sitting here and I came back in a few days, it's all gone. It goes from liquid to vapor completely. That's not an equilibrium. So if the system is open to the atmosphere, you're not going to have an equilibrium situation. So an example I had was, anybody remember what solid carbon dioxide is? Well, that's dry ice. If I have a piece of dry ice sitting here, it's eventually all going to turn into a gas. It's not going to have some solid and some gas. It would if I had it in a closed container. That would be dangerous, by the way, because it's a gas. So this is not an equilibrium. Eventually, all of it is going to turn into gas. And lastly, okay, the last thing I'm going to show you here is a prelude to the math, is how do we measure an equilibrium? Okay, so I'll show you this, and we'll probably end up calling it a video. How we express the position of an equilibrium. Is the right side of the equilibrium favored? What does that mean? That means that the products in general have higher concentrations than the reactants. Similarly, are the reactants favored? Like a weak acid, the reactants are favored. How do we measure that? Is there a number we can put on? Well, yes. There's two numbers, actually. There's Q, which is called a reaction quotient, non-equilibrium. That's called a reaction quotient. It's a ratio, which I'll show you here in a minute. K is really what we're more interested in. That's at equilibrium, and that's called an equilibrium constant. I'm going to show you this, and then we'll see how far you can get. This should take you through problem set number 1. Okay. And let's keep it generic. I could keep using the same examples. Let's consider a generic equilibrium. So I've used this before. A moles of A reacting with B moles of B in equilibrium with C moles of C and D moles of D. Just generic, it doesn't matter. Some balanced chemical equation. Okay. Q equals the concentration of chemical C, so I'm writing that really big, raised to the C power. So the C here is the concentration of the chemical. The little c up here is the coefficient. So it's pretty easy. Times the concentration. Oh, I made a mistake. It's actually a really important mistake. Brackets indicate equilibrium. Parentheses indicate non-equilibrium. Okay, so what is this? This is a ratio, and you could probably write this, of the products divided by the reactants at any point, not necessarily equilibrium. The thing to remember, it's products over reactants. So if Q is a really big number, that means that the products are favored because the numerator has to be bigger than the denominator. If Q is a really, really small number, then the reactants are favored because the denominator is a really big number. So just kind of think about what that means conceptually if it's a big number. And if Q equals 1, well then they're about equal concentrations. But that's a very unusual thing to have happen. But anyway, products over reactants. The equilibrium constant is exactly the same thing except it's equilibrium concentrations. This is more what we're going to deal with, equilibrium concentrations, because Q is the conceptual thing. Okay, so this is called reaction quotient, non-equilibrium, equilibrium constant, equilibrium, and I'm going to leave this up to you to think about what these mean. If Q and K are the same numerical value, that implies you have an equilibrium. Okay, so if these two ratios are the same, the system is at equilibrium. If Q is less than K, what does that mean? So Q is less than K. That means that this number is smaller than that number, so yeah, let's see. That means that you have to have more reactants in equilibrium. I'll let you think about that one. Okay, so that means that the denominator here is bigger than the denominator here. So there's more reactants. This denominator is just bigger. Well, what has to happen? Well, you have to get rid of some of those reactants. So some of the reactants, because the denominator here, these are the reactants, some of those reactants have to go away. How do they go away? Well, they shift and form more products. And that's called a so if this, okay, so the equilibrium will have to shift to the right in order to reach equilibrium. A cheap way of remembering this is a really cheap way. If Q is less than K, just follow the direction of the open mouth. You have to have a shift right. I think that's going back to when you learned about what greater than and less than equals. So the opposite is true here. You have more products. That's going to take some time. Le Chatelier's principle, Q's and K's, are a little abstract. Use the book, and I think this takes you through to most, not all, of your homework problems. So that's the content for equilibrium. We're going to come back and do the math in another video. So that's a ton to deal with, and I'll upload this, well, when you're watching this, it will have been uploaded. So take care, and most of the videos are not going to be anywhere nearly this long. All right, folks, we'll see you back online.